So, Dean, we were talking a little bit ago that a new series of stamps is announced that includes images that were taken from the SDO, or the Solar Dynamics Observatory. Just tell us a little bit about how that came to be and what some of those images actually are.
So I'm really excited about this, to have SDO images on a series of postage stamps. They're quite colorful. They represent various things that we see on the sun. Some are solar flares, which are really just brightenings of a small part of the sun. But others are also these large prominent eruptions that we see where an arc of material just erupts off the surface. And they're pretty amazing to watch. And we have some lovely movies of them that the one stamp is part of. It's just one still from that movie. But they're all related back to sunspots. And we've seen sunspots for 400 years. People have been drawing them in notebooks. And now we have fine photography of sunspots in many observatories. But of course, I like the SDO sunspot pictures the best because, well, they're just the best.
And along the lines of these photos, I assume you guys aren't just up there to take photos. Can you tell us a little bit more about the broader mission of the SDO, what kind of information you guys gather, and how that is helpful to the public?
So the goal of the SDO, and actually much of solar physics, is to understand the sun's magnetic field. Here on Earth, we have water. Water is liquid, gas, and solid. And our weather is determined by whether it's in a gas phase, liquid, or a solid. So on the sun, we see magnetic field as kind of that what determines the weather on the sun. When there's a strong magnetic field, we will see a sunspot at the surface, and we will see above that sunspot arcs of material moving along the magnetic field. When the magnetic field gets too strong, and then it will cause a flare to happen, and the magnetic field will lose energy, but we'll see the energy come out as the bright lights and particles of a flare. And eventually the magnetic field gets wound up into these prominences and just basically gets thrown off the sun because the sun can't think of any other way to get rid of the magnetic field it's produced. So although we think of the magnetic field as kind of the way weather runs on the sun, it's not the same kind of process. The sun basically creates magnetic field and then gets rid of it. And that getting rid of it is what we're interested in, because the solar flares produce energetic photons and particles that fairly quickly make it to the Earth, about 8 minutes to get from the sun to the Earth. And there they can affect our communications, they can affect our satellites. But the real thing is when these prominences get thrown off, or the filaments get thrown off the sun, then they move out through the solar system and they can strike the magnetic field of the Earth and cause us problems that take a long time to heal and can cause power outages, especially in the northern latitudes, and other problems here at Earth. So we want to learn where the magnetic field comes from, how does it arrange itself on the surface, how does it get dissipated, and how do those things propagate out to us and affect us here at the Earth.
Speaking of tracking those solar flares and magnetic events, and of course the images, can you tell us a little bit about what the SDO actually is and how it's gathering that data?
So SDO is a satellite. It was launched back in February of 2010. It has 3 instruments. One of the instruments measures things like the sunspots. It basically takes pictures of the sun in which we see sunspots, but we can also see the velocity of the sun's surface. So we can measure the sound waves, which, much like an ultrasound of the sun, allow us to see inside the sun and under things and around things. As a matter of fact, we can use those sound waves to see the far side of the sun today. So we can analyze the sound waves we see today and see what's happening on the far side of the sun. We also use that instrument to measure the magnetic field of the sun. Then we have a second instrument that measures all of those colorful pictures. 9 of the 10 colorful pictures come from this other instrument that we call AIA. And it measures the very hot material that's suspended above the sun in what we call the corona. And it measures a variety of temperatures from about 50,000 Kelvin up to about 7 to 10 million Kelvin temperature. And the idea of measuring all these different things is that we can watch material get heated. So it goes, we see it in one wavelength where it's cooler, and then we'll see it in another wavelength where it's warmer. And so we can watch it get heated up. We can watch it cool back down after a flare. So the idea is that we can build a model of the magnetic field, watch it go through a flare, and then produce artificial observations that we then compare to the AIA observations. And it's working quite well. AIA, the combination of AIA and the magnetic field instrument called HMI have produced some great models that are just now starting to understand how flares happen and how the sun reacts to them, which is one of the basic ideas behind all the instruments on SDO. And then there's a third instrument that measures the sun as a star. It looks at the entirety of the sun, not as an image, but just treats it as a point. And we use those measurements to understand how the sun is going to directly affect the Earth with those radiation.
So it sounds like in the years this has been operational, it's already been quite successful. What would you consider the ultimate successful outcome for the project as a whole, based, I guess, on the successes that it's already had or what you guys have coming in the future?
So our ultimate success would be understanding how the magnetic field of the sun is created, arranged on the surface, and then destroyed out in the corona. And we keep getting close to one part of it, and then when we draw back, and then somebody notices something else. So I think that if in general we create the ability to study all the different examples so that we don't miss what the sun actually does that's important. Because one thing we've noticed in the past is people looked only at events. They wanted to see the biggest event. SDO has allowed us to look at all the events that happen on our side of the sun for 11 years now. And by doing that, we don't miss the details. We see all of the storms that happen on the sun. And so people can start dividing them up into categories and understanding that how this category is a little bit different than that category. And if at the end of SDO, we are now able to understand why a flare gets triggered, how the flare puts all that energy that we see into the various pieces, I would think that we were a pretty good success. But we've already been a success. We understand much more what's going on inside the sun. We understand what's happening on the outside of the sun. And as a scientific research satellite, our goal is not to find a final product. Our goal is to develop the understanding of the interior of the sun, the corona of the sun, and then give that information to other people so they can understand how it affects us here at the Earth.
Great. Is there anything else that we haven't touched on yet about the mission with the SDO or these new stamps that are coming out that you would want the public to know? I think you said they're available in June, right?
I believe they told me June of 2021, so I keep telling people they'll be available at about the solstice, the summer solstice this year. I think it's great to have stamps that illustrate some science for the people in the United States. And I hope that, like the eclipse stamps that came out in 2017, that celebrated the total eclipse of the sun. I think that the SDO stamps celebrate our incredible advances that we've made in understanding the sun using satellites like SDO and the other satellites of the fleet that we have out in space. So the cool thing about SDO is the stamps are static, but each one of those stamps has a movie associated with it. And really, it's the movies that show you why we study the sun. These things, they're kind of weird looking, and you can't imagine how the sun gets to some of these. It's like watching a contortionist. How did the sun ever get to look like that? Well, we have movies that show you how the sun got like that. And so those are really what SDO was built for, was to show the time dependence and get away from just being static pictures. But I would like to just show you my favorite, because you never let somebody go without seeing your favorite. So if I can share my screen. So if we see, this is a talk that I gave some time ago. And this is my favorite eruption on the sun. I call it the trebuchet eruption because it looks like a medieval siege weapon erupting over on the right-hand side where all the bright loops are. And it's resetting now. And then it'll go there. You can see the nice hook.
Oh, I see.
And
it's
so
kind of got an arc to it before it throws the.
Yep.
What is that? Is that plasma, I would assume?
That is plasma. It's about 50,000 Kelvin. So it's about 100,000 Fahrenheit. And that is actually a small eruption on the sun. We just happened to catch a very nice, we got a nice view of this one. So, if you depending on your orientation, you get better or worse views. This is just one example that shows the complexity of what we are trying to understand on the sun.
And you said that would be considered a small eruption.
And that is a small eruption, yes, sir. The one that's called plasma blast is a large eruption. That one occupies about a third of the circumference of the sun. So that one's a pretty large one. The largest we had wrapped all the way around, it took up almost 2/3 of the circumference of the sun.
Wow.
So now you see why people study it. It's just, here's your opportunity to study something that's just beautiful and amazingly complex.